In the past few videos, we've been talking about line integrals over plane curves. And now I'd like to talk about line integrals over space curves. And put simply, we do exactly the same thing, it's just now with one more variable. And so I have a path in space. So some curve R. I imagine chopping that up over its arc length. And so each individual length I could call a delta S sub k. I then take a sample point in each subinterval. And in the kth subinterval, I could let that be x sub k, y sub k, z sub k. And what I do now is exactly what I did before. I'm going to imagine taking the function, plugging in the sample point, and multiplying it by that width. I add all of those up. And so I'm just repeating the same process, though I've lost the ability to visualize it as a wall in 3 space. Though I could imagine it as a wall in 4 space. That might be a little difficult, but that's okay. And now what I do is I do the same thing I do for every definition of the definite integral. I take a limit as the number of intervals in my partition goes to infinity, or the width of each one goes to 0. And this defines the line integral over the space curve C. Okay, so there I have a definition, and of course, this definition works only when that limit is defined. But just like with plane curves, right, this is a definition. How do we evaluate these line integrals? Well, we do exactly the same thing. This line integral over the path C is equal to the integral from a to b of f of x of t, y of t, z of t, times speed dt, because the same relationship exists between ds dt and speed in space as it does in the plane. So this is how we'll evaluate a line integral for a space curve, and it's really the same thing we were doing before for line integrals over plane curves.